Welcome to our channel Circuits Analytica. In this video, we will discuss voltage divider biasing circuit. A bipolar junction transistor must be in active region to operate as an amplifier. To keep a BJT in active region, its base emitter junction must be forward biased and its collector base junction must be reverse biased. Different types of biasing circuits are used to bias a transistor. DC load line of a BJT amplifier is the plot between minimum and maximum values of VCE and IC. For the proper functioning of the transistor amplifier, that is, to amplify both halves of the input signal for a sine wave input, the operating point of a transistor must be fixed on the center of the DC load line. During the DC analysis of the voltage divider biasing circuit, we have to find the values of VCEQ and ICQ. To find the value of ICQ, we must find the value of IBQ, as ICQ is equal to beta times IBQ. So here VCEQ and ICQ are the voltage difference between collector and emitter when there is no input signal, and current flow through the collector of the transistor when there is no input signal respectively. Similarly, IBQ represents the base current of the transistor when there is no input signal. Voltage divider biasing circuit. So here the resistor network R1 and R2 divides VCC to a lower voltage. That is why this is called as a voltage divider biasing circuit. Resistance RC is the DC load of the circuit, and resistance RE is the emitter resistance, which provides stability for the circuit against variations in beta and VBE. This is the most widely used biasing circuit. The performance of this circuit is better than the performance of the other biasing circuits. The circuit is also called as a self-bias circuit. Now, to do the DC analysis, we have to apply the Thevenin's theorem. After application of Thevenin's theorem, circuit shown on the left-hand side becomes as shown on the right-hand side of the screen. So, according to Thevenin's theorem, any linear network can be represented as combination of a voltage source VTH in series with a resistance RTH. So this is the network. The first step is divide the network into two networks, network A and network B. Here we have to apply Thevenin's theorem to network A. So next step is to disconnect network B from network A. So now network B is disconnected from network A, and find the open circuit voltage VTH. Open circuit voltage of network A is nothing but the VTH is equal to IR2 into R2. So same current flows through resistance R1 and R2, which is equal to VCC divided by R1 plus R2. Therefore, we can write VTH is equal to VCC divided by R1 plus R2 into R2. Next step is to find the Thevenin's equivalent resistance RTH. So Thevenin equivalent resistance RTH can be found by replacing all independent sources with its internal resistance. So here there is only one independent source, independent voltage source VCC. VCC is set as 0, or voltage source VCC is replaced with its internal resistance short circuit. So when voltage source VCC is replaced with its internal resistance, circuit becomes two resistors connected in shunt. So RTH is equal to R1 parallel R2. Therefore, we can write RTH is equal to R1 R2 divided by R1 plus R2. So now we can draw the Thevenin equivalent resistance of network A as a voltage source VTH in series with resistance RTH, where VTH is equal to VCC divided by R1 plus R2 into R2, and RTH is equal to R1 R2 divided by R1 plus R2. So this is the voltage divider biasing circuit after replacing network A with its Thevenin equivalent. So now let us apply KVL to the base emitter loop of the transistor. VTH minus VRTH minus VBEQ minus VREQ is equal to 0, where VRTHQ is the voltage drop across Thevenin equivalent resistance when there is no input signal. VBEQ is the potential difference between base and emitter of the transistor when there is no input signal, and VREQ is the voltage drop across the emitter resistance RE when there is no input signal. So we can write VRTH is equal to IBQ into RTH. VREQ is equal to ICQ plus IBQ into RE. So we know that ICQ is equal to beta times IBQ. Therefore, we can write VREQ is equal to 1 plus beta into IBQ into RE. VTH minus VBEQ minus beta IBQ plus IBQ into RE minus IBQ into RTH is equal to 0. VTH minus VBEQ minus beta IBQ plus IBQ into RE minus IBQ into RTH is equal to 0. VTH minus VBEQ minus beta plus 1 into RE plus RTH into IBQ is equal to 0. Therefore, we can write beta plus 1 into RE plus RTH into IBQ is equal to VTH minus VBEQ, where VBEQ is the voltage between base and emitter when no input signal is applied, and IBQ is the base current when no input signal is applied. Therefore, we can write IBQ is equal to VTH minus VBEQ divided by 1 plus beta into RE plus RTH. Equation number 1. Now apply KVL to the collector emitter loop of the circuit. VCC minus VRCQ minus VCEQ minus VREQ is equal to 0, where VRCQ is the voltage drop across collector resistance when no input signal is applied. VCEQ is the voltage difference between collector and emitter of the transistor when no input signal is applied. And VREQ is the voltage drop across the emitter resistance RE when no input signal is applied. We can write VRCQ is equal to ICQ into RC. VREQ is equal to ICQ plus IBQ into RE. that is equal to beta IBQ plus IBQ into RE. So VREQ is equal to 1 plus beta into IBQ into RE. Therefore, we can write VCC minus VCEQ minus beta IBQ plus IBQ into RE minus ICQ into RC is equal to 0. VCC minus VCEQ minus beta IBQ plus IBQ into RE minus ICQ into RC is equal to 0. We know that ICQ is equal to beta times IBQ. Therefore, VCEQ is equal to VCC minus 1 plus beta into IBQ into RE minus ICQ into RC. So using equation 1, 2 and 3, we can find the operating point of the transistor. So here VCEQ is the voltage between collector and emitter when no input signal is applied, and ICQ is the collector current when no input signal is applied. Thanks for watching Circuits Analytica. Enjoy learning.